Welcome to this institute. This is our third event in the 2017 University of Southampton Environment Lecture Series, and tonight we're going to focus on the oceans and climate. So my name's Professor Rachel Mills. I'm the Dean of Natural and Environmental Sciences at the University of Southampton. I'm going to host you this evening. I'm going to introduce the speakers, and I'm going to corral the questions and make sure everybody gets a voice who wants to. Tonight we've got three experts who are going to speak to you. We're not going to take questions till after they've given their talks, and then we'll take questions during the panel discussion. So I'm just going to say a little bit about the university and why we're hosting this, and then we get on to the main event. So the University of Southampton appointed the UK's first professor of physical oceanography, who was called Professor Henry Charnock, in 1966. That's just over 50 years ago. And since that time, we've grown our capability in ocean sciences, and the National Oceanography Centre, Southampton, where some of us today work, is now one of the largest marine institutions in the world. We study the world's oceans, and these themselves have changed substantially in the last 50 years. We are pumping nearly 10 billion tons of carbon into the atmosphere each year, about a quarter of which ends up in the ocean. If we look back to 1966, the atmospheric CO2 levels were around 324 ppm. They're now over 400. So that's a substantial change in those 50 years in the atmospheric CO2 that we're experiencing. That increase is not slowing down. So the oceans are warming as a consequence of these CO2 emissions, and this warming leads to rising sea levels. It leads to melting of the ice sheets in the Arctic and Antarctic, you're going to hear about tonight. These warmer oceans may or may not lead to more extreme weather events. We're going to hear about that tonight. And they lead to changes in ocean currents, and they have a sustained impact on marine life. But warming is not the only issue we need to deal with. Ocean chemistry is changing. It's becoming more acidic, the pH is dropping, and the consequences of this disturb our biogeochemical cycles in the ocean, and we're now seeing the impact of this on each trophic level in the food web in the ocean. So in this session, our experts will explore the challenges and the innovative approaches that they have developed to understand and predict change into the future. They're going to introduce us to some cutting-edge technology. They're going to talk about the measurements they make, and hopefully about the vital importance of coordinating our national efforts and international resources so we can maintain and develop ocean monitoring and predict the future. Okay, so now I'm going to introduce our first speaker. So please join me in welcoming our first keynote speaker. Eleanor Frajka-Williams works at the University of Southampton, and she's going to deliver her keynote lecture, Observing the Ocean Circulation and its Role in Climate. Okay, a little bit about Eleanor. Eleanor is an associate professor in physical oceanography at the university, and she spends significant time each year at sea making hugely important measurements of the ocean. She uses our cutting-edge technology and instruments to measure the small changes and larger changes in ocean circulation. And she has pioneered the use of the UK's autonomous underwater fleet, including boating at Boatface, that I think you're going to hear a little bit about tonight, to make measurements in the icy Southern Ocean. She combines observations from satellites, where data is captured from the outskirts of the planetary atmosphere, and small boats deployed into the ocean to track and follow ocean features to look at these weather systems in the ocean. This year, Eleanor was recognized by the European Geophysical Union General Assembly as the Outstanding Early Career Scientist in Ocean Sciences 2017. Welcome, Eleanor.
Thank you very much for the introduction. So, my name is Eleanor Frajka-Williams. I'm a physical oceanographer, as Rachel said. And I'm going to be talking about the role of observing the oceans in understanding the role of ocean circulation in the climate. And so one of the key areas that I'm going to talk about is how we use ocean observations to better understand the physical processes that are occurring in the ocean, and in particular, so that we can better represent these in climate models. I'm not going to be talking about climate models. I'll leave that to our next speaker. But in order to represent physical processes in the models, we have to have a good understanding and representation of the physics in the models. So I'm going to highlight a couple of areas which may seem a bit remote in the middle of the North Atlantic and down around Antarctica, but it's really these lower frequency, longer term changes that occur in the oceans that are setting some of the tendencies in the climate system. So not the fast response weather that you may experience in the day-to-day, but what happens over the longer timescales. So just to start off, because I'm not going to talk about this too much, I just want to highlight that ocean observations are incredibly important in order to assess the state of the climate. And a wide range of multinational efforts go into making observations to document how the oceans are warming, how that warming is regionally different, so different regions will warm at different rates, and all of this in response to what we may think of as climate change or global warming, which is the effect of the increase in greenhouse gases, CO2 in the atmosphere, on increasing the total heat contained in the Earth's system. And so this plot here just shows temperature percentiles, which is just indicating what regions in the oceans and on land as well are particularly warm or particularly cold. And you can see that this is for January to June 2015. Across most of the globe, you see red, but there are a couple regions where you see blue. And so the efforts put into just assessing the state of the climate are monumental and cannot be discounted, but I won't be spending a lot of time talking about it. Only to say that these observations are made from a wide range of satellite observations, autonomous profiling floats, and ship-based observations in order to just see how the heat content in the oceans is changing. And 90% of the increase in heat due to greenhouse gases is stored in the oceans. So in this talk, instead, I'm going to be talking about using ocean observations to set a benchmark for understanding different processes in the climate system, so the strength of the circulation, the large-scale ocean circulation, and also how ocean observations that may seem relatively localized can be used to improve our physical understanding of processes in the ocean that may be too small to directly represent in climate models. And so only by developing this physical understanding can we then have a way of putting these processes into the climate models to see how they behave over the longer timescales. So in order to talk about this, I'm going to talk about something that's referred to as the Great Ocean Conveyor, or what we usually call either the global or the meridional overturning circulation. Meridional in this case just means north-south, and let's see if this, and it refers to the large-scale circulation of ocean currents. So you may have heard of this. Sometimes people talk about the shutdown of the overturning circulation or the shutdown of the Gulf Stream. They really should refer to it as overturning circulation. But this schematic here shows just a simplified version of what's going on. So these red bands are indicating ocean currents in the top roughly 1,000 meters of the world's oceans. And the arrows are trying to show the direction of circulation. So you have northward flowing water in the top 1,000 meters going up the Atlantic. And then this water, when it reaches the subpolar regions, which is around us here in the UK, or just south of Iceland, it undergoes a process called transformation, which really just means incredibly intense storms come across from the northern part of Canada. They release a lot of heat from the oceans into the atmosphere, and then that heat, when it's lost from the oceans, results in the waters becoming dense. And when they're dense, they sink. They sink to 2 kilometers or deeper, and then this water forms what's called the deep western boundary current, which comes back south. So this Great Ocean Conveyor has a number of important roles in the climate system. In particular, it went through this transformation process at high latitudes. When the waters sink, they store residual heat, they store carbon and properties in the deep ocean, but also in the process of coming north and carrying relatively warm equatorial waters up here towards us in the UK, they help keep our climate locally more temperate. It's a bit tricky to try and see what this is doing. So this is an attempt to visualize in 3D. This is a spatial plot showing circulation around Antarctica and connecting to the Atlantic section. But you can also take a section, a depth latitude section, so going north, south, and in depth, and stretch it out here and see what the ocean is doing subsurface. And so this can be useful to see this northward flowing water. This is intermediate water and also surface waters. The transformation processes that occur at high latitudes, so then the water comes south in the deep western boundary current, and then also, which I'll talk about later, some of the processes occurring in the deep ocean. And this circulation system you may have heard about in the popular side of the media, the movie The Day After Tomorrow, which is now a number of years old. It starts off with a scientist giving maybe a sort of dull talk but showing a circulation diagram kind of like this. So I like this movie. And then a little bit later into the movie, he starts throwing up his hand saying, oh no, we're losing our data sources from around Greenland. This one's wiped out, this one's wiped out. All these real-time data sources that we get, they're cutting out. It can't be an anomaly. And then within a few days, all of New York freezes, and Mexico is blocking the Americans from coming south. And so this is, I like that part as well. So this is a movie that's depicting things that are unrealistic because it's Hollywood. So the changing on the order of a couple days and all of New York City freezing over, that's not realistic. But it is based in some science. And trying to understand what happens if the overturning circulation that we observe in the ocean slows down or shuts down is an important part of understanding how the oceans are playing a role in climate. So this is just an example of a scientific version of the day after tomorrow and what happens if you shut down this ocean circulation. It's on two different time scales. So the top panel here is showing in a numerical simulation of the oceans what happens if you shut down the MOC. And if you shut it down for 100 years, what you see in particular is a very cold region, including over the UK, the southern tip of Greenland, maybe not New York, so they got their geometry a little bit wrong there. But it does actually show an incredible warming. And if you look at the color scale on here, this is in terms of degrees. So you see a significant cooling in these regions in the North Atlantic when you shut down the overturning circulation. And then when you look at present-day observations, so this is the same picture that I showed you earlier, you see something curiously similar. There's a cold patch in the North Atlantic. It's been referred to in the literature as a cold blob and has led a number of scientists to question and investigate whether this is a sign of the MOC already slowing down. So due to its importance in the climate system, there's this large-scale ocean circulation, and we want to know how it varies in time. Before we get to that though, there is the question of can this really happen, and if it does, how does it occur? One of the ways, so I said that when the water gets to the northern regions, it loses a lot of heat to the atmosphere, and by cooling the waters, it becomes more dense, allowing them to sink. But if you add a lot of fresh water to the same region, you can prevent that sinking from happening. And if you remember from this plot here, these regions where this water mass transformation occurs are near Greenland and the Arctic. And you may have heard that the Arctic has been losing sea ice, and Greenland has been melting at increasingly fast rates. So there is this source of fresh water, which is one of the favorite ways, at least in numerical simulations, to shut down the circulation. So due to its importance, the UK and the US have been monitoring the strength of the circulation now since 2004. So it's the past 13 years in the North Atlantic, and in particular between Florida and the Canary Islands. The way that you do this is by making a lot of observations. A large team of people go to sea every 18 months. They change out instruments, these ones here, hundreds of these instruments that are, the useful bits are on the inside, but they're in titanium housings to withstand the extreme pressure in the deep oceans. Hundreds of these instruments are deployed on what are known as moorings on the western side of the Atlantic, on either side of the Mid-Atlantic Ridge, and on the eastern side of the Atlantic, where these are made up of flotation. So like these orange spheres here, or the larger one down here, they have instruments along the way and then a large anchor at the bottom. And by combining these observations of the ocean properties, temperature and salinity, you can make an estimate of how much water is going northward and southward. So this is an incredible effort and has been underway now for the past 13 years to measure the strength of both the northward circulation and the southward circulation coming south at depth. And the results from this have been really astonishing, actually. So if you look at this, and you haven't seen something like this before, I'll just explain what you're looking at here. This is a time series of the strength of the overturning circulation in this light pink color over the past, this one ends in 2014, but at each point in this graph, it's telling you on that particular, this is about a 2-week time period, how fast was this water moving north and south. The units on here look a little bit obscure. There's in something called spheredrups, where 1 unit of a spheredrup is 1 million cubic meters of water per second moving northward. So here, if we have a value of around 20, it means there are 20 million cubic meters of water moving northward, 20 million cubic meters of water moving southward. The astonishing thing about this is the range that is observed in the value of this circulation, as well as the frequency, how wiggly or how furry this line looks. And after the first year of these observations were published, so just in 2005, it really started to make people question how they viewed this ocean circulation and what its role was in the climate system. It had previously been thought of as this relatively slow, sluggish ocean current moving north and south, and now you see that it varies very quickly. After a few more years had been recovered, it actually started to change the way that this circulation was represented in numerical models. So previously, with the expectation that it's a slowly varying current, the simulations would only typically output an annual value for how strong the circulation was. And after seeing the wide-ranging fluctuations, they started to output it more frequently. So these kinds of observations, which take a lot of effort, a lot of investment by both the US and the UK, have been incredibly useful, both in setting how we do climate science and in understanding what we see in the ocean and how that compares to numerical simulations. And in this case, this ocean circulation, because of its importance in the climate, has been in the focus of the IPCC reports, so these large international panel reports on how the climate is doing, where the climate models almost universally predict that the circulation will slow down in the next century, but they disagree on when and by how much. And so time series like this, made from the observations, can be used to provide a benchmark for numerical simulations, can, in this case, change how those numerical simulations are run, and then can provide a check for whether or not models are capturing the short time scale and the 10-year fluctuations correctly and for the right reasons. So this is one of the uses of ocean observations in understanding climate. The next one is similar. It's at the southern end of this same circulation pattern. And in this case, it's in a region around Antarctica where deep water is formed. So we had deep water formed up here in the North Atlantic, and that was the source waters for this part of the overturning circulation. This is now the source waters for the lower limb. So the Weddell Sea is in the Atlantic sector of the Southern Ocean. So it's tucked in south of the Antarctic Peninsula here, just south of Drake's Passage, where these two land masses come together. And in this region, you have, instead of atmospheric forcing, you have ocean ice forcing that can cause dense water to form due to when ice is forming, salt is injected into the ocean. This water then becomes what's called Antarctic bottom water, and it spreads northwards into most of the world's ocean basins. So at the deepest layer of most of the world's ocean basins, you see this water mass. Now, over the last few decades, observations of this water mass have shown that it's been warming, and through warming has been contributing actually to sea level rise, even though this water mass is more than 4 kilometers below the surface of the ocean. This panel is just showing across the globe, waters deeper than 4,000 meters and how they're contributing to sea level rise in each of these sectors. And if you look at it, you can see, well, the North Atlantic in this case, below 4,000 meters, it's not doing too much. But below 4,000 meters, most of the activity, so the reds and a couple of blues, are concentrated around Antarctica. And maybe it looks like the ones around here, this is the Weddell Sea again, are showing some of the brightest reds. So this is a large-scale pattern of sort of long-term decadal changes, and we want to understand how these changes are coming about so that we can have a better handle on how they may change in the future. This is where Bodie McBoatface comes in. So this project is called Dynamics of the Orkney Passage Outflow, and this is a different sort of a study to the observations, the continued observations of the overturning circulation. This is what's known as a process study, where you go in with a team of people for a shorter period of time, so localized in space and time, and make really intense measurements to try and capture all the scales of variability that are relevant to the process that you're looking for. So in this case, preliminary evidence had shown, well, from the large-scale picture, this pattern of warming around Antarctica, and then preliminary evidence localized around this region called Orkney Passage, which is in the extension of the Antarctic Peninsula, shows that the pattern of water mass changes in Antarctic bottom water north of the passage compared to south of the passage appeared to be due to wind forcing, even though these waters are, again, 4,000 meters, 4,000 meters of water separate the atmosphere from these deep water masses. So that sparked interest in doing a more targeted, focused experiment in this region, and that's the one called Dynamics of the Orkney Passage Outflow. And for this, we just completed the fieldwork in May of this year, so there's a bit of an ice picture, although this one was actually 2 years ago, where moorings were installed in Orkney Passage, so 2 years ago during this time period. These moorings have been making observations in this narrow choke point where the Antarctic bottom water flows out of the greater Weddell Sea into the northern part and the rest of the world's oceans, to complement, so 2-year time series of these, to complement spatially resolving high-resolution observations during that 8-week cruise. So taking these two things together, and I'll just keep talking while this hopefully plays, you can get a picture of what are the small-scale processes and the changes that are occurring in this focused narrow region to try and better understand how it may be imprinting onto the larger scale, decadal scale changes that we see. So this is just an animation showing what Boaty McBoatface did on its 3rd mission during this cruise. The little circles are showing relative temperatures. So the red bits are relatively warm, the blue bits are relatively cold. Here it's coming out across Orkney Passage, going back again. The arrows are showing velocity is measured from the same thing. This is an animation of JCR getting in the way. And then if you look at the whole swath, what this autonomous vehicle actually did over the course of 3 days was it went south, well in this case south, and then north, and then south, and then north, following isobaths and making measurements of ocean properties, ocean velocities, and also turbulence as it went. And by picking apart some of these patterns that are really unprecedented scale for horizontal scales, we can get a better handle on what appears to be a wide range or a zoo of small-scale processes involved in mixing and water mass transformation at the deepest layers of the ocean where these currents are rubbing up against topography. All right, this was in case the video didn't work. Okay, so targeted observations can allow us to develop our physical understanding of processes that really are not represented in climate models, and we can then try and understand whether it's something that is likely to have an impact on the large scales and longer time scales. I think I'm out of time, so I'll just finish with this, which is just saying that as we come upon more and more observational challenges to try and make observations of the ocean at the space and time scales at which it's varying, so the important scales to observe at, there are challenges like large chunks of ice falling in the region where you want to get up close to the front of a calving iceberg, and technological solutions that may make themselves available include tiny little versions of autosubs. This is a 4-kilogram underwater autonomous vehicle that has a potential to be launched from an unmanned aircraft. And then here, this is a project going out in November where we're using satellite data to see how the eddies are coming into the Bahamas. Hopefully no more hurricanes. Eddies being sort of like underwater whirlpools, and then going out and observing them with another flavor of autonomous underwater vehicles. All right. Thank you very much.
Thank you, Eleanor. And it's great to see, hot off the press, this is the future of oceanography. These really clever measurements, these really high-scale measurements, these autonomous vehicles are where we're going to be in the next decade, 50 years, etc. Anyway, on to our next speaker. I'm really delighted to welcome Professor Stephen Belcher. Stephen is the Chief Scientist at the UK Met Office, and he's going to deliver his keynote, The Role of Oceans in Weather and Climate Forecasting. Again, a bit about Stephen first. He leads a team of more than 500 research scientists at the Met Office, and he's recently become the chief scientist. This team has earned a worldwide reputation for excellence in weather and climate science, in particular the translation of science into weather and climate services for daily weather forecasts, emergency responses, and mitigation and adaptation to climate change. But particularly relevant for our discussion today, Stephen led the Met Office Hadley Centre as they move to focus on climate science and services, where they provide governments and industry and society with what he calls actionable advice or climate services. So we're really excited to have Stephen join us here tonight to share his thoughts about forecasting weather and climate. Welcome, Stephen.
Great, thanks Rachel. It's a real pleasure and honour to be invited to give this presentation this evening. So I thought that following on from what Eleanor told us, and that was a real voyage of discovery, I think, through the world's oceans, I'll give you a flavour of some of the ways that we use these ocean observations and this understanding of the ocean in forecasting, both in short-range forecasting, in longer-range seasonal forecast, and then a little bit on the climate end. So in preparing for this presentation, I was thinking, well, it's pretty obvious what the big weather story has been this year, I think, if you think worldwide. So this is Hurricane Irma, and I thought I'd just say that I got a text from a friend of mine from university who I hadn't seen for 20 years. I thought, this is very strange. This man is suddenly very interested in me. And it turned out he'd heard about my new job. I moved to be chief scientist 6 months ago. And he was on Cuba, which is just off the map here. And I think he saw an image a little bit like this, and he wanted to know what was going to happen. So I pointed him to the Met Office website. So this is a fantastic satellite image that is showing Hurricane Irma as it makes landfall over Barbuda. It's a false colour image that shows us the clouds that were going on during this. So there's the thunderstorm clouds. We've got cirrus outflow here. Just exquisite detail. And you probably remember that Irma had sustained wind speeds, meaning more than 1 minute, of 185 miles an hour when it hit landfall. So imagine cycling against that. I sometimes complain about a headwind when I'm cycling on my bike, but I've never had that. So here are Met Office forecasts. One of the aspects of hurricanes that the Met Office is called on to forecast is, of course, the track of the hurricane. And what you're seeing here is a range of forecasts at different lead times. So the black symbols here are showing where the hurricane actually tracked. The red line is an early forecast, and then as we go along through these figures here, you can see more and more, later and later forecasts, so started a day later in each case. So you can see the original track was going to go up on the east side, of the Florida Peninsula, but actually within about 4 or 5 days of warning, we saw the track going on the eastern side. So this was really quite a predictable hurricane, actually, in this case, and gave, as I say, quite a bit of warning. My friend happened to be on the south coast of Cuba, so he got out okay, as far as I know. Now, where do the oceans come in here? Because the track is largely steered by the large-scale wind patterns that advect or carry the hurricane around and take it on its path. But the oceans also play a really important role in hurricanes. So I don't know how well this has come out. It's come out better on my laptop here. This is the next one in the chain, Jose. Out in the Atlantic. So Jose was here, so we're not able to see the sea surface temperature because of the cloud cover. But due to some clever post-processing done at the Met Office, the colours here are showing you the sea surface temperature. So Eleanor was looking under the surface. This is just the surface sea surface temperature. So red is relatively warm. And what you can see here is that Jose is leaving a cold wake, a wake of cold water behind it as it tracks towards the west here. And so what we know is that hurricanes need energy. So a hurricane is a region of 1,000 kilometers across or so of spinning air. And the energy derives from the heat in the surface ocean being taken into the atmosphere and spinning up that circulation. So as it does so, it leaves a cold wake behind. So the ocean is limiting the growth of these hurricanes. So the intensity of hurricanes is intimately connected with the efficiency of that heat transfer from the ocean. And in fact, so far in the Met Office, we don't account for that limited heat storage. So we just take observations of the sea surface temperature and just allow the hurricane to get as much heat as it possibly can out of the ocean. But the new generation of models will have to account for this and will actually limit the strength of the hurricanes that we see from the forecasts. Now, it turned out in Irma was moving relatively rapidly, so this limit on the strength was reasonably small, But some of the other hurricanes that we see that stall over the Caribbean, it's a much bigger effect. So we need you guys in Southampton University and NOC to help us with that side of things. So thinking now, so that's this kind of weather forecasting application. Thinking now of longer lead time forecasts. This figure here was put together with colleagues who are going to just on the panel. I think, Bablu, you were involved in this, at National Oceanography Centre and also within the university. And this shows how the way we represent the ocean is really being revolutionised right now. So when we do our long-range forecasts and our climate simulations, we have a simulation of the ocean and a simulation of the atmosphere, and we have to join them together. We've known about atmospheric processes for quite some time now. We've had good models of them for coming on for 50 years now. And the atmosphere is a relatively well observed part of our climate system. But the oceans are relatively poor cousins here. It's partly because of the observations, and Eleanor's technology is giving us serious insights there. But also our modelling technology, the way we simulate the oceans, is nothing like as well advanced as the atmosphere. So in our climate simulations, this is our representation of the ocean here. And you should be able to see the coastline has got relatively jagged lines there, indicating the level of pixelation that we have in these models. The pale colours here are a proxy for the ocean currents. So Eleanor focused on the large-scale overturning north to south in the oceans. There are also more surface gyres which carry water across the oceans in a clockwise circulation like that, which is what these white lines are showing. And on the right-hand side, in the way we represent these in the climate models, you can see it's incredibly smeared out. In the new generation of climate models that we're just working on right now at the Met Office, you can see we're getting these spaghetti-like panels which are much more faithfully representing the kind of turbulent aspects of this ocean circulation. And the interaction between these turbulent eddies and the large-scale circulation is a real focus for attention at the moment. And then on the right-hand side, on the left-hand side here, you can see that we're much more fully resolving the richness of those eddies. And this is an experimental simulation. I think we've done 30-odd years now, Bablu. So this is really a test bed for what we might do in the next generation of simulations. So what we've done with that, so Met Office we've just installed a new supercomputer, so it's the largest weather and climate supercomputer in the world. If you have the right adjectives, it's the largest in the world. It's not the largest supercomputer. To run these simulations is computationally fantastically expensive. So these models produce petabytes of data every day now. So just handling that data and piping it around and turning it into services is a whole kind of area of investigation in itself. But this new supercomputer has enabled us to represent the ocean in a better way. So here's a similar plot to what I was showing before. This is now the eastern seaboard of the US with Florida down here, and the colours indicate the surface temperatures in the Atlantic, so warm near the tropics, cold up near the poles with a gradient, and parts of the meridional overturning we see here. When we go to this quarter of a degree so-called ocean model, you can see the coastline is much better represented, and the seamounts under the water are much better represented, so the pathways for the water there are better captured. But you can also see we're capturing this richness of the dynamics that we saw on the previous figure, and this extension of the Gulf Stream here, or the meridional overturning here. Now, this region is particularly important for UK weather because it's off the eastern seaboard of the US and over this part of the Atlantic that we get our rainstorms, particularly in the winter. So the mid-latitude depressions with their cold and warm fronts tend to form just off the eastern seaboard and form over this region. So by capturing this greater variability and detail in the ocean gives us a better representation of the way those storms develop and how they aggregate over seasons. So using this simulation with an atmospheric simulation, we've now had a real breakthrough in forecasting winters for the UK 3 months ahead. So this is terrible timing, Rachel. Next week I'll have the forecast for this coming winter, but can't give it to you now because we don't have it. And so, in particular, one of the things that we're now able to say is give a probabilistic forecast for whether the UK and Europe in general will generally have warmer, wetter winters for the specific winter, or colder, drier, so the cold, high-pressure regions that give us this frosty, kind of pleasant summer, winter days. So it's that long-range forecast giving us, will it be a colder than average winter or warmer than average winter, that this is really unlocked. And we're looking into summer predictability now. It's much more challenging, but we have a paper on the stocks for that Martin will want to take a look at, I think. Sure. So I've talked a little here about the short-range forecast, talking about the hurricanes and how they get heat from the surface ocean. Here's an example on the seasonal forecast timescale. So the ocean's the part of the system that has the memory that gives us forecast skill on those longer forecast ranges. And then finally, I'll just say a few words about climate, so picking up on some of the things that Eleanor introduced earlier. So Eleanor showed you maps. I'm going to show you this well-known time series going from 1850 up to present day. And it's the warming we've seen in the global mean temperature since a proxy for pre-industrial times. So another friend of mine's a historian, and he's not too chuffed with climate scientists calling the period 1850 to 1900 pre-industrial. I think he has a view that the Industrial Revolution may have got underway by then. So we choose this period because it's as far back as we can reliably go with different data sets, etc., etc. So we take that as our baseline, hence temperature was 0 then, that's our baseline. And we see the warming through the 20th century, so a relatively rapid warming in the first few decades of the 20th century, relatively flat period that's not often talked about during the war and the immediate post-war periods, a very rapid period of warming in the 1970s, 80s and 90s, a period in the 2000s which is much talked about, when the warming slowed down, and then the last 3 years we've seen record-breaking temperatures, again a resumption, a return to the high warming rates that we were seeing here. Slightly forgotten what I was going to say next. Okay, so one of the things that we've been studying a huge amount in the Hadley Centre over the last few years is to try and understand this period during the early 2000s, over here, when the warming stalled. There was a lot of discussion, the global warming has stopped, is it all a fix or a hoax? So understanding what was going on there in the context of this longer term warning has been a really important part of climate science for the past 5 or 10 years. So in order to understand that, oceanography is really central to this endeavour because the ocean again brings the long scale memory into the climate system, at least on these decadal timescales. So this figure here shows you a plot of the average sea surface temperatures during the period 2014 to 16. So this is the period just after when we saw this big leap out of the slowdown in warming, when we saw accelerated warming. And the experts in the audience will see warm sea surface temperatures in the Pacific. So many of you will be familiar with the El Niño phenomenon, which is a slow mode of climate variability where we see warm temperatures in the Pacific, which lead to weather systems or impacts on extreme weather right across the world. Over this longer period, we also see warm temperatures up on the western coast of the United States and Canada as well. And this pattern is known as the Pacific Decadal Oscillation. So climate scientists like oscillations, and they like giving them 3-letter acronyms. So this is the PDO, not to be confused with the AMO or the NAO or all the other O's. This is the Pacific Decadal Oscillation. And on this figure on the right here, I've superimposed on red is the global mean temperature again. And the blue is an index of this Pacific Decadal Oscillation, which is an index of that sea surface temperature pattern in the Pacific. And what you can see is that early in the 20th century, Pacific Decadal Oscillation had a positive index, went negative during the mid part of the 20th century, positive again during the period of rapid warming, was negative in the early 2000s, and has now made a switch into positive. So this Pacific decadal oscillation is very highly correlated or related to these periods of rapid global warming and relatively flat global warming. And so what we understand now is happening through a combination of observations and climate model studies is that this pattern of sea surface temperatures is taking the heat from the surface ocean, subducting it or moving it down to depth, and sort of hiding, if you like, the warm water from the surface. So it's not appearing as a warming in the surface temperatures. So we're not seeing it as part of the surface global warming, even though overall the oceans are warming. So seeing this return to a positive index of this Pacific decadal oscillation, we think in the Met Office that this period of slowdown in global warming is at an end, and we're resuming to rates of warming that we saw in the late part of the last century. Finally, further evidence that the global mean temperature is just one indicator of climate change. This figure shows sea level rise. So Eleanor alluded to this. So of course, sea level rise is likely to be one of the most pervasive and constant aspects of global change that we're seeing through anthropogenic climate change. So here is observations of global sea level rise rather than the maps Eleanor was showing us, going from 1900 through to present day. So the earlier period, it's a remarkable technological achievement, this actually, and I know there are some experts in the audience, so I'll tread with care. The early records, I think, were largely made by tide gauges, so this is sort of seeing us back to a race of seafarers, and then in more recent times we have the satellite era. But taken together, there's a very consistent message of sea level rise, really a monotonic, a very consistent sea level rise of 2 or 3 millimeters per year on the global scale, and not subject to those fluctuations we were seeing in the global mean temperature record. So sea level is projected to continue to rise, and actually it's one of the most uncertain aspects of climate change projections, sea level. There's many things we don't understand about that, and this is the global mean. When it comes to the regional patterns of sea level rise, I think we understand even less. But one thing's for sure, the sea level is going to continue to rise, and we will need to think hard about that. So finally, just bringing this back to the UK, one of the richest observational data sets of sea level rise actually is the one that the National Oceanography Centre, which is, of course, a close cousin of the University of Southampton, looks after. So because it's a regional signal, there are more wiggles on it, but again, we see this persistent rise over the course of the 20th century out to present day. And information like that is used. So one of the fun things about the Hadley Centre is that this science is used for practical applications. I worked in universities for most of my career, and one of the things that attracted me to the Hadley Centre is that we can use this information. So we participated in a study to look at the long-term value of the Thames Barrage, which is the picture on the left here, and the degree to which that will be able to protect London from storm surges as sea level rises. And actually the conclusion there was a good news story from climate science, that the present protection is sufficient, we believe, to withstand a one-in-a-long-time event. Okay, so to wrap up, I hope I've convinced you, I'm sure I didn't need to, the oceans are a critical part of the weather and climate system. The oceans provide this long-term memory, which is in fact what gives us the ability to forecast months, seasons ahead, and it's clearly an important part of the climate system. So really, for us in the Met Office, working with Southampton Oceanography Centre and the University of Southampton is absolutely critical. We get our ocean simulation model from the university and NOC. So without you guys, we wouldn't be able to do this forecasting that we do. And with that, I'll end. Thank you.
Thank you, Stephen, and I'm looking forward to that winter forecast. So. Finally, let me welcome Professor Dr. Martin Visbeck. He's going to deliver his keynote, Human-Ocean Interactions, What Will the Future Ocean Look Like? So Martin Visbeck heads up physical oceanography research at the Geomar Helmholtz Center for Ocean Research in Kiel, Germany. He's another seagoing scientist with a long and distinguished record of expeditions across the oceans. He makes observations of the changing oceans on short and longer timescales. He coordinates big international projects. He serves on important global committees. He's developed a significant voice with the United Nations, communicating our ambition for sustainable development. He's also the lead of the Future Ocean MOOC, the massive open online course. This MOOC has attracted thousands of learners from around the world to study why the oceans are so important to us all. And we're particularly excited to work in partnership with Martin because we have a MOOC exploring our oceans, and we'd like to work with you to understand how this online delivery can impact and inform governments and society worldwide. So we look forward to hearing about your thoughts on the future of the oceans. Welcome, Martin.
Well, Rachel and University of Southampton, thank you very much for inviting me to London today to speak to you about the human-ocean interactions. So what we're trying to do is, although I am a physical oceanographer and I very much relate to the two presentations, but I'm actually going to step back a bit and look at the same system more from a humanities perspective. And I'm going to start with 4 images. Up on the left, that is not Kiel. I wish it was. Stephen, which country is that? You should read tabloids more often. So, Prince Albert, Charlene, the twins, come on, Monaco. So this is the Mediterranean, and Monaco is a pretty much thought after place because I understand that taxes in Germany and London in particular are pretty high. If you go and rent a place in Monaco and become a Monaco citizen, you can pay much lower taxes. That's why a lot of people build apartments, as you can see in this picture there. So the Monégasques got the land from France at some point, and I'm pretty sure if Prince Albert knocks on the door of the French and said, "Can I have more land?" the answer will probably be no. You know, we still regret it that we gave you the land at some point because now you become a European tax haven. So what Monégasques and people do when you run out of space on land, you think about moving into the ocean. What you see here is a city planner study from the Monégasques, which are actually thinking about moving part of the city, the development of Monaco out into the ocean. It's one ocean future. Down there you see a hotel in some nice coral reef, and we can discuss the future of coral reefs later. That subway is so old and ugly, but I don't know, it's not my picture. But on top, what's that? So here's another dimension of ocean and climate and future, where some engineers think we're going to build big research vessels, much bigger than the James Clerk Ross, to actually heat up the seawater and generate water vapor, which has salt crystals in it, in some parts of the atmosphere where we have a reduction of cloud condensation nuclei. By actually putting these salt crystals in the air, you're going to increase the amount of clouds. Why would you want to do that? On land, people do it for irrigation purposes. But on the ocean, there's enough water. Why do you want more clouds? And it is to control the planetary temperature. It's these efforts that are called climate or geoengineering, where some people think we're going to use the ocean to cool down our planet. Again, another future of the ocean. Now, most futures that we see look a bit more like that. You go to the beach, you go to harbors, and the ocean looks pretty used by humans, some say maybe overused, and we're going to address these two challenges, the prospects and the challenges. Now, we do this in Kiel, like Southampton, we're at the sea, and what we have the benefit of to have a world-renowned research center like Geomar, but also the university with all its faculties, and as Rachel was saying, we're benefiting from economic perspectives, from policy perspective, from philosophical perspectives, and I want to show you a little bit about the science that we do with that network. I'm going to start with a chart like that, which sort of looks a bit more beautiful on my screen, but I think you can kind of make out the continents. And every red dot means a lot of people live there. Southern England and London shows up as pretty red, so does maybe the Netherlands and parts of Germany. And the squares, the black squares, are major cities. But even looking from the back, you see most people live on the coasts. In fact, 40% of the world population is no farther away than 100 kilometers from the coast. 13 of the 15 megacities are coastal cities. So the things that we just heard in the two previous talks, sea level rise, any challenge from the ocean, will be getting to humanity very quickly because we like the ocean. Let's take another look at humanities. How many people are on this planet? When I was born, there were 3 billion. Today, we have 7.5. So in my lifetime, Stephen, in our lifetime, Rachel, our generation, we doubled the people on the planet. We doubled. That is pretty amazing. Why did we do that? Because we had access to cheap energy. We managed to get food security. Fertilizer is a big factor in that. And also we managed to cure diseases. So that's what we see is enormous growth on people on the planet. And if you look at UN projections, they're somewhere between 10 billion, is the most likely number. It could be 16, could only be 6, maybe, depending on how the nations behave. But a growing population certainly puts increasing demands on the environment, including the ocean. So if you keep that in mind, and then you take an outer space perspective and say, okay, 10 billion people, 1 planet, 1 ocean. Now, the space agencies tell us, Stephen Hawking, I think, right? He was just talking about just months ago that I think in the next generation we should move out to some other moon or some other part of our solar system or even beyond. Personally, I'm not so sure that that's going to happen, so we maybe get stuck with this 1 planet, which has 1 ocean. And if you think about that, how we're going to develop humanity, I think we need to respect the ocean or planetary boundaries. And this chart shows you the various dimensions. We talked about climate and climate change already. We can talk about ocean acidification on the panel and what it does to corals. We can talk about the amount of fertilizer that we're using, overusing of nutrients. Some of that get into the ocean, cause changes there. But I like the Oxfam version of that. So there are things around us, 1 planet, 1 ocean. And in the middle, there's humanity. Everybody on the planet wants water, income, education, resilience, voice, jobs, energy, social equity, gender equality, health, and food. Growing that ambition to 10 billion, what is the safe and just operating space for the planet, and what does it mean about ocean? So I think for the university, Southampton, wouldn't that be a great motto? A leading question for the university, what is the safe and just operating space for humanity? I think that is a great question for the knowledge system of universities to tackle. And yet, if you look at German universities or UK universities, they're busy with lots of other things. But they never really say that, although I think that is a good question. Now let's make this ocean. Elements of sustainability. Ocean is life support system. Oxygen, food, biodiversity, climate stability we discussed, but also sense of place. Clearly, ocean, with us living near the coast, is supporting our life. And we saw some dimensions in the first 2 talks. I want to talk about sense of place. If you go to some beautiful island, make your pick, maybe not the one where the hurricane just came, let's say Bermuda, and you check in the hotel, they might ask about your passport and your credit card number, but probably pretty early in that list, they ask you, do you want a room with ocean view or garden view? Rachel, what do you choose? I mean, you say, hey, I went all the way to the ocean. I want that ocean view. And the guy says, well, it's sort of going to be 50 pounds more expensive. You're like, okay, doesn't matter, right? I went all the way. I want to look over the ocean. So it's interesting that the fact that we look over the ocean is valuable to us. We're actually willing, at a very personal level, to shell out quite a few more pounds for such an ocean view. And I tell you, if you come to, let's say, Shanghai, go for garden view. Definitely go for garden view. That ocean view is not that you want to pay £50 extra. In fact, it's probably cheaper. Europe, UK, we need economic growth in our societies. That's what humanity tells us. And so we are all looking to the ocean to solve our economic growth problem, don't we? Have you heard about this blue growth agenda in the UK, in Germany for sure, in Europe? And it's about income, markets, jobs, technology, and what is it? Is it about fisheries, oil and gas, renewable energy, transport? What is the biggest blue economy around ocean? Any guess? oil and gas. That could be true for the UK, although I'm not sure. I'm sure it's probably true for Norway, but I can tell you for Germany, for Europe, for the US and China, it's none of them, it's tourism. And my guess is it'd be a close second or maybe even before oil and gas in the UK. Now, if tourism is the big blue growth business, what does that tell you about the future of your ocean and seascape? You want it fully industrialized, or you want it beautiful and clean to enjoy for the next generation of tourists that pay that extra £50 for that hotel? Ocean and societies. It's about equity, quality of life, diversity of cultures, institutions, and governance. And I usually spend a bit of time talking about German history on oceans and societies, and I won't, but I'll just say seafarers connect the world. The UK has a very strong tradition of seafaring nations, and anybody who has a seafarer in their family knows they're much more worldly people. They've seen different nations, different countries, that connection. If you live in our countries these days, that connectivity has good things for transport and has challenging things for people. We don't like those people so much that come over the ocean and want to go into the UK or Germany or Europe, these refugees from Africa, right? And yet the ocean does connect us, and the refugee is part of that challenge. So we, a few months ago, put together an ocean atlas that talks about that human and ocean space. It's the ecosystem services that sustain life on the one side, ocean and seas for us as a service, the blue service for man and society, and yet we are challenging that services by things like climate and climate change. Stephen told us about sea level rise. Certainly pollution, we haven't mentioned that yet. We're on the climate side here, but certainly that's well known with all of you. Destruction of coastal environments, overfishing, things like that. So it's this interaction. On the one hand, we need the ocean for our survival. On the other hand, we're not always treating it nicely. Now, at the international level, we're thinking about this 10 billion challenge. And the Agenda for Sustainable Development, the 2030 Agenda for Sustainable Development, is all about people, us, our prosperity, peace, partnership, and the planet. Fortunately, the planet. Out of these, we developed 17 Sustainable Development Goals. So these are the ones that are supposedly capture the dimensions of our future. And there is one on fire, which is quality education. So I'm sure the University of Southampton wrote a couple of letters to the UN Secretary General and said, you've got to put that down, because that's what we do, right? Quality education. Now, there's also one on climate and on ocean. Did the UK government want an ocean goal in this negotiation about the future of humanity? No. Germany? Not really. US? Maybe. Because they said it's too many. We had 6 Millennium Development Goals, maybe we're going to have 10 for sustainable development, not more. Why do we have a Sustainable Development Goal for ocean? Think people again. United Nations, everything gets decided, almost everything, by unanimity, which means every country has a vote. There's many small island states, those who got hit by the hurricane and others, and they say our economic prosperity, our future depends just on one thing, and that is the ocean environment around us. So it's the small island development countries who put their foot down and said, well, I'm not going to have an ocean goal, won't vote for it. Germany loves the ocean goal. So does the UK these days. Germany loves it in particular because small island development states also have a vote for other things, like a seat on the Security Council, which Germany always wants, right? You need a good number of allies. So we work a lot with small island development states for our horse trading for security, which is okay. Climate is there as well. So it has some language, policy language, it has some targets, and it has, and I ask us, observations come in, how do we measure progress against these targets? And then they put some indicators down for ocean, and you all, if you ever read the policy text, you'd be appalled how poor the indicators are. None of them around sea level, none of them around ocean acidification, none of them around the things that we care about. There's a little bit about fisheries, and that's about it. Now that has to do with the way in which the United Nations makes these policies. It can only report global indicators that get channeled through the statistical departments of each and every country around the world. Not too many countries measure MOC. You can't have that one. So it's a challenge. Now, there has been a group who has developed an alternative index called the Ocean Health Index. And I like it because it connects the physical things that we discussed about, the ecosystems, the natural products, habitats, tourism, and so on. And you make an index for each coastal state. By the way, the globe is 60%, half full, half empty. But the map shows something revealing. It shows you the health of the coastal system around the planet. And it is not the industrial countries like Germany or the UK who are particularly bad. It is actually the least developed countries around Africa who have by far the worst environmental status. And that is because our global actions in these countries are much worse than what we do here. When we do oil and gas drilling in the UK, in the North Sea, it's all protected by lots of laws around it. There's a lot of security and safety in the operation. Pollution is not acceptable to us, all of that, all of that. The same country goes drilling in Angola. The local law says you don't have any law, so they do it cheap, they do it dirty, and that destroys those coastal environments. So it's interesting that the poorest countries by now already have the poorest environmental status in their coastal zones. So again, it's a global challenge. We have some responsibility here. I wrote a paper about the benefits of an ocean SDG, and I won't say much about it, rather than it does help rapid, because it gets into the policy sphere that ocean is important to them. It encourages nations and regions to think about the ocean space. They usually don't do that at the UN. The ocean is not one of the major affairs there. So I think it's a good thing. But it has a challenge too. Sustainable development has, as I said, 17 goals. And your foreign ministry has this big challenge now that they get asked to do everything. And it's the interaction of these goals, or what they call policy coherence, which makes this tough. Now, marine scientists say, great, we have goal 14, now we know what to do. You know, we stop fishing, we stop the climate change, we work on maybe sea level protections, can't do much about hurricanes, but maybe a bit more protections around that. So we have our agenda down. But you know, your foreign ministry thinks about these global challenges. How can I reduce poverty? How can I lift people into education? And so it's the interconnectedness of the goals that really makes it politically interesting. Which is kind of cool, because if you look at the ocean, it does a lot of things with other goals. And I'll show you in a second how it's connected. I did some work with David Griggs, who you guys know. He used to be in your position, I believe, at some point back, Mons Nielsen and myself. And we said, can we measure these interactions between the goals? It's really important for climate. For example, ocean and climate go together very well. But there's one goal that says affordable energy for all. Guess what? If you go down the silos, the best solution is give everybody coal. That's the cheapest energy on the planet. If you want affordable energy for all, you go coal. But then you say, whoa, I don't want to do that because it gets a lot of CO2 comes out, so you're going against the climate goals, so you're in conflict. Right? So managing this conflict and mapping this conflict is what we've done. And we actually did it for the ocean. It's interesting. The ocean has a big role to play for poverty because coastal fishermen have helped with the local poverty reduction. It has some role for food security, not in the UK, not in Germany. I think if you would stop selling fish tomorrow in the UK, nobody would die. I don't think anybody would really starve. That is very different in African states. So it has a role to play there and has many other dimensions. So this policy coherence is what keeps politicians quite busy. And I'm going to end with 3 comments on what I call the ocean value chain. Because I think the ocean value chain connects the talks and gets us into discussion mode. In Southampton, in Kiel, Rachel, we love discovery. Right? We love to discover the ocean. There's so much unexplored and undiscovered. So it's about observing, mapping, going out there with Bodie McBoatfair and other great things to see what's there. The deep sea biosphere is hardly understood, right? So that's what we got. We try to find new things. And once we found them, we're like, why? It's these processes, Eleanor, that you mentioned, this understanding of the processes. Why is certain things happening? That's what drives, I think, all of you at Southampton University, certain us in Kiel. And sometimes, Stephen, we get lucky. In some fields, in physical oceanography in particular, we can use our understanding, put it into equations, and train computer models so we can actually do forecasts. That's by no means easy in coral reef ecology. But in physical oceanography and climate science, that is a lot easier because we know the fundamental equations. It's more an issue of computer power, which you showed us so nicely what we can do. So it's the understanding, prediction, that's what we do in the sciences. those here in the room are not scientists at Southampton or at the Met Office. You're maybe in the civil, as a citizens, you're more interested maybe in the policy. Why doesn't anybody do something about the climate change issue, right? So, but politics and policy, they don't want to read the most famous paper of Eleanor and I. Eleanor, what is your most famous paper? Which one do you like better? It's probably in Nature or Science, because we love these journals because our administrators give us tenure for these, right? But if you go into the governing place, they're not going to read that paper, and if they pick it up, they can't understand it. So what they want is assessing the information, turn it into their language. In climate, we have the IPCC, the Intergovernmental Panel for Climate Change, who does that. For ocean, we have some things. It's only then that you are willing to maybe act or govern, once you understood the issue in a language that you can relate to. And when you want to do that, Stephen, you showed that. You have the Thames Barrier, and the people want to say, was it a good investment? And you could say, well, I wish we knew better what regional sea level looks like in the UK, which is the other answer to your question. And we know we don't really have the good answers for that just yet. So it gives you good motivation to go back to observations, improve your understanding, make better models to maybe give more precise answers. So putting logos around that. So the governing acting happens in the policy sphere. Sustainable development goals play a role. Assessment, there's a World Ocean Assessment. We can discuss that later. Nobody knows about it, although it's mandated by the General Assembly. Observing, GOOSE, Global Ocean Observing System. I work with this big EU program called Atlantis, GeoBlue Planet, global coordinated effort. Stephen, you gave the motivation for that. Services, ocean and climate services wanted globally coordinated observations. Understanding processes, the various programs we have, like CLIVA, the World Climate Research Program, SOLAS, IMBER, and so on, do that. And then at the service end, Europe in particular, also including the UK, we have the Copernicus services, the climate services, the ocean services, that take that knowledge and make it accessible for the policy and governing place. And there's international programs to connect to that. But I'm going to end with a couple of funny pictures. This is me at the UN in June this year, at the first ever United Nations Oceans Conference. So the SDG 14 guys were happy. We got the whole UN, to show our case. All the other goals are standing ready. We want a conference too. They won't get it. Amina Mohammed, the stalwart of the sustainable development process, said, sometimes you have to put your smallest cousin on stage so everybody knows she's there too. The ocean in the UN is a very small piece. So it was an awareness-raising conference there. But what we could do, there was a call for action. Rachel, did you respond to that call for action? No. It was a call for action. Everybody, civil society, business, governments could respond, and I'm sure the UK did. And we, as you just mentioned, we registered our MOOC. Because we thought, why not? We're doing a service to the global community. They can come and look at your MOOC, look at our MOOC. We just registered. It's a commitment. It costs some money, some effort. So we did, and because I like it so much, and Rachel mentioned it. Rachel, can I show the 2-minute as the last thing? We're done.
This is the ocean, vast and endless. It encircles the planet, covers 71% of the Earth's surface, and provides more oxygen than all the rainforests combined. It holds unmatched and sometimes untouched natural resources, more than we could ever imagine. Here life began and has been sustained for millennia, harboring secrets we have yet to unlock. This is the ocean, the source of food and energy and the highway for international commerce. Its shores are home to 40% of humanity that lives within 100 kilometers of the coast. It provides sustenance, livelihoods, and links our global economy. But this is also the ocean, a vast yet finite system bearing the telltale signs of our careless lifestyles. It is highly stressed through our growing interventions and is groaning under the burden of pollution and climate change. How can we be good stewards of our planet so that we and future generations can live in harmony with the ocean? Can we use our understanding of the ocean system and human system to change our actions to support human life within safe limits so that the ocean can continue to sustain its eco-services for us, as it has for so long? Come join us and learn about the ocean and what it means to you. When we put our knowledge together, can we use ocean system thinking to arrive at more sustainable, smarter interactions and solutions leading to better governance?
So as Rachel mentioned, we offered this MOOC twice already. We always had around 2,000 to 3,000 participants, and 400 or so finished the course, which is a pretty good ratio. 10% is typical. Personally, it gives me hope. What I saw with Eleanor, our increasing capability with robots to look at the ocean, to understand how it works, all the work that we do at the universities and centers to really dive into it, shine a light on that unknown space ocean, is a good thing. Understanding, predicting, allows us to more intelligently interact with us as society members, because they want to learn from us what is happening and what will the ocean look like in the future. Predictions, understanding is a big part of that. And I think if we collectively make our knowledge available to other citizens in the UK, in Europe, around in the globe, I think we'll probably get to a better solution on the governing and acting space. Because humans like to act if they know why and when, but we don't like to act in the absence of knowledge. So I think if we take this sort of knowledge circle serious and see our roles, I think we have reasons to be optimistic, although we can also be concerned because, again, 10 billion people on the planet all want the same lifestyle as we have here in this hall will be a challenge. So I'm looking at the University of Southampton for good solutions. Thanks for listening.
Okay. Okay.
Somewhere here?
Yeah. Okay, if our panel want to come and sit up here, we're going to be joined by two new people who you haven't seen so far. One of these is Professor Jörg Wiedemann, Professor of Biological Oceanography and Head of the Coral Reef Laboratory at the University of Southampton. And then we have Dr. Bablu Sinha, who is a marine systems modeler from the National Oceanography Centre. So if you grab a seat, I'll just ask Bablu and Jörg just to quickly say something about what you do. So Bablu first.
So Steve actually introduced me very nicely. So I work at the National Oceanography Centre, and I'm in charge of developing climate and ocean models, and we work closely with the Met Office on the models that he showed you.
Thank you, Bablu. And Jörg?
Good evening, I'm Jörg Wiedemann, and as Rachel said, I'm heading the Coral Reef Laboratory in Southampton, and we want to understand how corals respond to various forms of environmental stress and how that relates in changes in the ecosystem.
That's great. So I'm now going to open questions to the floor. If you stick your hand up, we'll bring you a mic so we can actually all hear you, especially the live stream. So if you could just say who you are as well, thanks.
Yes, I'm Martin Freeth. I make science films, basically, which means I know nothing. Now, the question really that Stephen triggered in my mind is when he said that around about 1850 or 1900, that was where the good data went back to. But surely we need data from, and have data from, 20,000 years, 10,000 years, 500 years, and it will be indirect and it will be dependent on geology and all kinds of things. But if you want to know about acidity, sea level, and temperature before 1850, can you count on any of that? Because you need that, don't you, to make your long-term predictions?
The answer is yes, but I'm going to let Stephen take that one.
Okay, yeah, thank you for that question and calling me out on that one. So there are some really interesting projects actually on this. There's some projects which take records from sea captains and sort of observations of opportunity and digitizing them. There's a great citizen science element to this, which is building up a picture that goes further back than that, and we know things like the Little Ice Age in Europe. But the limitation in the kind of analysis I showed is the lack of global data, global coverage, and the lack of really the time detail as well as the space detail you need. So typically that's why we stick with 1850, but of course data does go further back than that. I'm sure the others can comment too.
So, do you want to comment as well, Martin?
Yeah, I think that is a great question, and I do think, again, we've been here presenting mostly what we call the instrumental records. So you're basically trying to use direct measurements of temperature, in this case, in sea level, also direct tide gauges, which in the old days were done most for tides rather than for sea level change. But you can use other archives in the Earth system. On land, you can use, for example, peat moss layers, also in the UK. In the ocean, you can use sediments, which are accumulating very slowly. In the cryosphere, you can use glaciers, which are accumulating fastly, in particular places like Greenland. So these recorders of environmental states of the past can be used and interpreted for diagnosing environmental change. And I think there too, the future is brighter than it used to be. In the old days, you had a few records and you had to sort of make sense from a single record. Now we have more records, plus we have an increasing amount of capable climate models. So you can connect the observations from these archives with what a climate model simulation tells you what might have happened. You have a little bit of an idea how, for example, the radiation was changing with the seasons in the ice ages. So if you put these knowledge together, you can actually get much better idea of what probably the last 2,000, the last 10,000, the last 20,000, even the last few 100,000 years looked like. So, but it's this combination of these different aspects of playing together that allows us to be more certain about changes. As Stephen was saying, if you look at just temperature, I think the Central Inland Temperature Record is the longest one that we have, which literally builds it on a thermometer, but there's many other archives that environmental scientists use to look at climate at the past. Exciting science. It's very powerful, I would say. It gets powerful by the years as we learn to use them in combination, and it does help to check whether our understanding of the climate system, our coupled climate models are realistic, and in that sense makes our future projections a bit more certain because they're more rooted in a solid base of understanding.
Okay, and let's hear about the corals. Jörg, do you want to make a quick comment about corals?
Yes, so it's always interesting to ask the oldest members of the community who lived through certain events how it was. And you can do that with corals because some of them get very old. So big Porites corals, they get several hundred years old. And it's still the same individual, and they record climate conditions in their calcareous skeleton, so in the limestone skeleton that they lay down. Both temperature and pH are reflected in the chemical composition, and our colleagues are actually coring these corals and then looking back into time and drawing conclusions how the climate has changed over the last couple of 100 years.
Okay, let's take another question. Maybe, okay, do you want to wait for the microphone and just tell us who you are? Thanks.
My name's Benjamin. I work in coral reef conservation in East Africa, and I had a question for Martin though about a slide that he put up on global human impact. And so my question is kind of two parts. Do you know about Halpin's work and where he predicted because he used climate and pollution and overfishing and a large range of indicators and came up with a really different map to what you had. So I don't know if you know about his work and could comment on maybe how that map was created differently. It was Northwest Europe and China that were the worst in his analysis.
Yeah. So thank you for the question. So it pertains to how can we assess, say, environmental status in the ocean. And indeed, there are different approaches to do that. There's certainly, in the climate community, we might be just looking at physical things, temperature warming or loss of pH, maybe oxygen. Then people take more ecological indicators. I don't know exactly the work from the colleague that you mentioned, but this particular work from the Ocean Health Index uses 10 dimensions. They might not be your most favorite ones, but it's just 10 different ones. And they looked at these 10 dimensions because they said, well, from the ecosystem services that the ocean has to us as humans, they try to cover all the aspects of that. And again, it's debatable. And depending on how you choose your indicators, you might get a slightly different answer. I can certainly give you an indicator which looks very horrible in China and very good in the UK, and I could probably give you one that's the other way around. So with indicators, you have to be a bit careful, and that's why indicators are so much debated in the community. My plea is it would be good if groups like your colleagues, the Ocean Health Index, and maybe others here in the room, the University of Southampton, had a bit more of an effort internationally to really develop these indicators, to compare these indicators, to check them, to cross-validate them, and to say which indicator can answer which question. But this one gives you that idea, and I think also experience that I have. When you look at the coastal zones, in particular development countries are pretty bad. China doesn't look so good on that one either. But again, there's one or two things where China does look good. My main problem was that if you're an indicator aficionado, what they've done, they took the plain average of 10 indicators. Now, if you're a sustainability thinker, you say that's the worst thing what you can do, because a plain average allows for full substitution. That means if tourism is good, fish can go down. But you know that they're not substitutable, so you should use a different average. You take 1 over the index, weight that, and then average it again, so you get penalty much more so one index is bad. So these are aggregation issues. All I'm saying is there's, in my view, not enough work around indicators. In the policy sphere, that's what they want. Europe has, we have the environmental status, we have a marine framework directive, which is very complex, lots and lots of indicators, maybe the most sophisticated in the world, but it's so difficult that even Germany, which has a tiny coastline, a lot of money, can't even fulfill that, let alone Spain or other countries with a long coastal zone. So indicators, to me, are a very interesting element, because that's how science connects to policy, and I just miss, there's just so little work on this, which is just amazing. And yes, you might have conflicting indicators.
Very thorough. Okay, good. Questions from elsewhere? Here in the middle? There's a mic coming.
Hello, I'm Raven, and I want to ask a question according to the lectures before. The first lecture is about observing the ocean circulation and its role in climate. So we talk about the meridional, just the overturn of the currency of the ocean currency. And the second one is about to do some climate forecasting on the ocean. So the third one is to get used to live in the ocean. Like we have some imagination and we do some, we will have child. So as far as we know, we human being was evolved from the ocean. At the very beginning, we lived in the ocean, and then we just come to the land. It is something like we evolved. But if we come back to the ocean, does that mean we are degradation? Degradation? I mean, just we go backward. So I mean, just the two lectures before is talking about how to, with human being, how to take advantage of the ocean and to get rid of some accidents from the ocean. But the third one is about to let us to get back to the old age. So I would like to ask you, maybe is it very contradictory or something like that? That is my problem. Thank you.
Right, was that clear? Yeah. Okay, Martin, you go.
Great question. So the question is, so we come from the ocean, live on land now, and now we're going back into the ocean. You know, maybe. And I think what you raise is an interesting question. That is, you know, when we look at the discovery, of understanding of the ocean system, we make great strides. But it is true that I think humanity never really left the ocean. I mean, it feels like we're on land, but our lifestyle is always dependent on the ocean. But being more of us and being more tech savvy, we lose a bit that connection, that feel to it. And I think now in our most technology developed world, the question is, are we going to go back to the ocean in a sense? Are we going to use the ocean more, use some advantages of the ocean? Or are we going to distance ourselves even more from that and really think, well, the ocean can do whatever it wants to do. For us, it's just a place where we dump our garbage. You know, we might get some energy out of it, but we're really not treating it as an important space to us. So that is the big question that you could ask. It has other dimensions. I just want to give another plug for some of my colleagues in your university. If we were to do life science again, medical sciences, Stephen knows this. I mean, the most important model in life science is not a dynamical model. It's an animal. It's called mice. Mice, right? Every experiment in life science they do on mice these days. They have lots of knockout gene mice, all of that, right? If we were to do life science again, I think we would use marine organisms. We've learned by now that genetically, some of the sort of the, what do you call it, the polyps, genetically are much closer to human than the mice is. They're much simpler organisms. They have the same diseases that we have. So you can test cures on these simple organisms much cheaper than on mouse. But because this mouse industry is so much developed, we love mice in life science, right? but actually, if you would do it again after we understood the genome, after we look at similarities and differences in organisms, marine organisms are really exciting these days for treating diseases, but also probably as a source of new substances for food additives and certainly cosmetics, right? So there's a big resurgence.
Pass to Jörg, because I think
and Jörg, I'm sure, knows all about it.
Do you want to comment on that?
On the cosmetics?
Not the cosmetics.
No, but
indeed,
there is an anti-inflammatory compound which has been isolated from a sea fan, from a coral, and that is commercially available, and it's in a very expensive cream that is sold in the US. And you have to think of the coral reefs as this huge accumulation of biodiversity. So about 25% of all marine biodiversity live in coral reefs, and that's just about 2% of the sea floor. So all these different organisms, they are competing for space. And they do that by applying some chemical warfare, so they're full of bioactive compounds, and all of them are potential drugs because they act on other organisms. So yes, there's a lot of potential to retrieve very valuable substances from these ecosystems in the marine environment.
Okay, thank you. I have a question here from Twitter. Since we're doing this, let's get it read out. So Sarah George has asked a question for Eleanor. So, can you see a significant role for citizen science in collecting ocean observations, Eleanor?
So citizen science for collecting ocean observations. I've heard of a few examples of this. I believe in, maybe not so much in the physical sciences, although actually I've heard of some using dive computers to record oceanographic properties, and using citizens to record biodiversity metrics, so in particular areas, counting sea turtles or other creatures that they see. I don't know whether you would be able to use citizen science to get measurements 4,000 meters deep, however.
That's a challenge.
That may be outside of the reach of anybody.
Bablu, do you want to comment on this?
Just that I think the citizen science can play some key roles, for example, digitizing records. There are many, as Stephen referred to, there are many records of ocean measurements in the past which are not digitized. That takes a great deal of effort and can result in lots of mistakes in transcription as well. So if you farm that out to lots of different people and they come to the same results in terms of the transcription, then you've got much more confidence that you transcribe those records correctly.
That's great. And are there examples of where that's happening now? Can you?
Yes, there are. I'm afraid I can't quite bring to mind, particularly, well, you'd have to ask Nick Rayner and others at the Met Office. I don't have the exact information now. But
something just ran across Twitter with that, of digitizing climate records.
I think Martin knows the answer. Do you?
Well,
no,
I'll give you 3 examples.
Okay.
I think the first citizen science project in physical oceanography were those citizens who live and work on the ocean, which were seamen. And we discovered and even measured quantitatively the strength of the Gulf Stream by bottles with cards in them. That was the first international experiment on measuring the strength of the Gulf Stream, and it ran for, I believe, 10 years, between 1908 and somewhere around then. And it was literally seamen threw bottles overboard. It was recorded on the little card in the bottle, where the bottle was thrown in, and when they saw a bottle somewhere else, they picked it up and wrote it down. Definitely citizen science. They were not scientists. They were citizens of the ocean, making their knowledge available for the scientists who then took all these data, put it together. A more recent example, which is so when what we do, that is kind of hard stuff, right? You go in the deep ocean and you need high-tech equipment. But we also, when I do my CDD measurements, I have ecologists on board and they take pictures. They want to just have pictures of deep sea creatures, shall we say, right? Now you have lots and lots and lots of pictures, you don't know what it is. So we have, if you go on our website, you can just help them to identify these creatures. You can sort them into different types of living species, and people love it. You know, it's like, you know, one of these software that I'm gonna, you know, you swipe left or right, you like it, don't like it, right? But that's what they do with creatures, and it's really wonderful. We use that concept from identifying stars and Milky Ways from the astrophysicist. And the third example I'm going to give you, we have a big program, extremely successful with school children, not so much on the physical side, but more on the pollution side, where we collect the garbage on the beach, and they not only collect the garbage and put it in the trash bin, they actually count it. And this program is citizen science. The schools do it in Chile, in Germany. I believe the UK is a partner in that, and I think Spain and some island in the Pacific somewhere. And the kids love it, because they can compare the trash they find in Kiel with what you find around the planet, and the scientists get a nice sets of plastics and other trash in the ocean. It usually runs once a year for a particular week, so it's a nice comparative study. So I think there's ample opportunity for citizens to get involved, but maybe not with Boaty McBoat Fair and some of the deep CTDs, but certainly with the ocean and marine science. It's very exciting, and people love it.
Okay, thank you. Stephen.
Yeah, the one I'm aware of, we had a collaboration with Oxford University on the simulations of future climate called climateprediction.net, and we took one of the Hadley Centre climate models and turned it into a screensaver. So in the downtime on your computer, you could simulate what a future climate might look like, and the reward is your machine might actually produce the right answer. Then again, it might not. So this produced actually millions of simulations, which has been an incredible resource over the last 5 or 10 years. So there's a lot of good examples, I think, in this subject.
Right, there's a question down here. Can we get a mic to her? And then... Thank you.
Hi, I'm Sally Jensen, the Climate Group. Thank you very much for all of your talks. I have a question particularly for Professor Stephen Belcher. You started your presentation off talking about Hurricane Irma and the ocean effect on hurricanes. I read something fairly recently that said there may even be the possibility of sort of predicting earthquakes such as the one that we saw in Mexico. I mean, it might not have so much to do with oceans, but, you know, to do with like deep sea ridges. I'm not a scientist myself, but I was wondering if you had any comment on that and the potential predictions for other types of natural disasters.
That's a big question. So I think when you look at the evolution of weather forecast centres over the last 50 years, it's evolved from my childhood, where there would be a man, and it was usually a man, stood in front of a board with some magnetic symbols telling you what he thought the weather might be like. Now we try much more to convert that knowledge of the weather into what the actual hazard might be, or the risk to you. So the Met Office teamed up with the Environment Agency to convert heavy rainfall into flood risks, for example. So there are other hazards that we try and forecast. The Met Office is focused entirely on weather and climate hazards. So the solid earth hazards are totally outside my sphere of expertise. And there may be better experts on the panel. I'm looking at Bablu to comment here. My understanding is that with earthquakes, it's particularly difficult to do a prediction any time ahead. So it's much more of a risk-based assessment. The chances are enhanced. But maybe just to finish this line, one of the new services we are looking into is solar storms. So as we rely much more on electronic equipment and satellites particularly orbiting the planet, a solar storm, so clouds of charged particle that come off the sun, and there are these big ejections very occasionally of charged particles, could conceivably have quite a big impact on the world. So it's actually on the UK's national risk assessment now. So we do have a forecast service that gives about 20 minutes of warning if one of these things would take off. So we observe the sun and we would see one of these storms coming, and that would give us 10 to 20 minutes of warning.
So, Bablu, do you want to say something then, Martin?
Yeah, sure. I mean, after that challenge from Stephen, I have to say that I'm not personally aware of any current methods of predicting earthquakes, but the closest thing I can think of is tsunami warning systems. So if there are earthquakes, subsea earthquakes, then they often, as we know, create tsunamis, which can be quite devastating. So we now have more sophisticated networks in place for dealing with those sorts of...
Martin?
There's actually some really exciting research happening on that very question that you asked. For example, indeed, earthquakes are hard to forecast, in particular in this sort of deterministic way that you would want to safeguard humanity. On the other hand, people who look at the causes of earthquakes, it has to do with certainly the plates as they move. And there's been an increasing science that looks at, are there certain times also in Earth's history where plates move more or less? And it seems to be that the hydrological cycle, the availability of rainfall, is a factor in that. In particular for shallow earthquakes, where a dry or a wet slip zone has a different resistance in the geophysics of the plates. So there's an increasing research that says a moist climate has an increase, I think, for slip failures compared to a dry climate. And so the research is, as this climate is changing, as we heard from Stephen, and also the hydrological cycle is changing, so dry places get drier, wet gets wetter on average. And what does that mean for the risks of earthquakes? And so there is an interesting science around that. The same is true for landslides and also subsea slides. So that connection, so that the climate or changing climate preconditions a certain area for increased risks, that is an interesting one. That doesn't help you with the concrete prediction of when an earthquake happens or a landslide goes off, but that preconditioning in the risk management is very important because it basically gives you some idea about when you want to get people out of their harm's way, building codes, things like that. So it's an interesting science, and indeed there is an increasing amount of evidence that that's probably true, although it's very hard to do with earthquakes in particular because they don't happen so often and all the details are not fully understood, but it's active research on this.
Okay, let's move on. Any more? In the blue at the back, yeah, thanks.
Hi, I'm Flo, an alumni for the University of Southampton. I have a question that's perhaps linking Eleanor's and Stephen's research together. You mentioned the role of observing the ocean to better understand what's happening in them and hence making more accurate forecasts. In an ideal world where we can spend endless amounts of money on gathering data at sea, is it possible that we have at one point enough data so that the model forecasts can be, if not 100, maybe accurate to a large extent, and we can accurately predict perhaps 10 years in the future? Thank you.
So unlimited resources for observing the oceans.
200 pounds.
Yeah. I think my gut reaction is no, that we wouldn't be able to improve forecasts to an incredibly high degree. Part of that is that how these processes are represented in models at the smallest scales, even if we, so the smallest scales, when we make these measurements, for instance, on Bodimek boatface, we're measuring centimeter scale fluctuations in ocean turbulence and how the smallest bits of water are moving against each other. This is something that's never going to be directly represented in a climate model. So to translate information about general patterns of very small scale fluctuations into something that can be used in a climate model, you still have to do some sort of physical and likely also statistical representation of these processes. So that's going to introduce some uncertainty along the way. But I think, well, with unlimited resources, you could certainly narrow down regions that are going to have a large influence that we can't yet make direct observations of important processes. I don't know, maybe you have a different answer. Maybe the forecast will be perfect.
Perfect forecast, yes, Met Office Chief Scientist says. I'm not going to fall for that trap. So we've got some experience in the atmosphere. So we use observations of the atmosphere to initialize the models, and then you march the models forward in time. That's a forecast. The atmosphere is much better observed, so when we get the opportunity of a new observation, we can test the impact of those new observations on the quality of the forecasts. So in principle, that would be the systematic way of understanding the impact of future observations of the ocean. I think it's fair to say, and I'll invite Bablu to comment later, that At the moment, our observations of the ocean are so sparse, we are so far from that new observations are very welcome. There was a turning point about 20 years ago when the so-called Argo float got launched. So, okay, you're nodding. These are things about my shape, about 6 feet tall, quite skinny, that go up and down the ocean and make profiling measurements.
But one person can easily chuck them over the side.
Right. Unlike me, yes, now I get it. So there are now several thousands of the Argo floats, but they tend to stay in the top kilometre. They're beginning to go thank you, beginning to go deeper, so the deep ocean remains relatively sparsely observed.
So that's a fair comment. I think in some ways... Oh, I'm sorry. In some ways, I turn your question around. We don't have unlimited resources, so what's the best use we can make of the resources we have? And there I'd sort of plug the models, which in some ways owe a debt to the observations. Eleanor mentioned that we were surprised when we had all this variability in the overturning, but now our models have caught up and they're very, high fidelity, and so you can actually use those to target questions like where would you make the best use of the observations that you can make, how often would you need to sample, which regions of the ocean would you need to sample, and the deep ocean is clearly a key one. And you can think of a few others close to the boundaries, for example, where the floats can't go, but which are very important for the overturning.
I'm going to just disagree slightly there.
Ooh, good.
So I agree that the models have much improved, particularly if you use as your metric the comparison with the overturning circulation at 26 north. But I would argue that it's very dangerous to then say, I'm going to use this model to try and understand where to make the best observations for understanding how the oceans are changing, particularly in that I think there are very few models at present that capture the 10-year trends that we see in the 26 north observations. There is a Met Office assimilating model that does capture it, but generally I think ocean state estimates, ECHO doesn't get it. I don't think NEMO 12th degree models get it. And so if you say, based on agreement of the seasonal cycle and the large dip events that we had in the time series, that the model is doing a good job representing it, I think you may be missing out on some of the longer term timescales.
Can I just quickly come back? I mean, I don't want to turn it into a big argument, actually, but so the key thing is to... I think the key thing is to recognize where the models are useful and where they're not. So, for example, the models may tell you where the eddy energy is, for example. So those sorts of things you can then target. Similarly for process studies and so on.
Pablo, I think they can't hear you.
Oh, sorry. Yeah. So I was talking about the higher resolution models being able to capture the eddy energy and also sea level variability. So it's targeting where the models are useful and assessing where they're not. I agree. Yeah.
Okay. Martin, really
Can I make
quickly,
one outrageous comment? I think if you would triple the observations in the atmosphere and you would triple the observation in the ocean, you see a huge increase in ocean predictability and not so much in the atmosphere.
Stephen, do you agree?
Wow. Gosh. Well, I think we are agreeing, because I think we're saying that at the moment the ocean is so undersampled that it would be a great investment. And we haven't talked about biological observations of the ocean, where a lot of the atmospheric carbon ends up.
I'm going to have one more question, and then we're going to adjourn and carry on the discussion over drinks. So any more questions? This one just here. Yep. Sorry.
Hey, thanks for your talks. My name's Sophia, working at the University of Reading and the Met Office. And maybe related to that, I wanted to ask about how important you think high-resolution climate models are. So I know you had a comparison in one of your slides, mainly Stephen I'm talking to, and I was in the next generation of climate models. I believe it's rumoured to stay at 1 degree instead of improving the ocean resolution to 1/12. And I wondered what you think about that. And also on looking at observations, how far are we away from having high-resolution global observational data in situ rather than from satellites?
Okay, Stephen first.
Okay, there are many other experts on the panel on this section of this So when we build the climate models to project long-term climate change, there's a tension. So we have a computer that can do a certain number of calculations. So the question is, how do we spend those calculations? We can either increase the fine detail, the resolution in the models, or we can increase the number of processes in the models. So one of the reasons we do climate simulations is to understand how much warming. One of the aspects of the warming is how much of the carbon dioxide we emit stays in the atmosphere. And in order to understand that, we need to understand the carbon cycle of the planet. So the amount of carbon taken up by land-based plants and also ocean biology. So the process elements, the complexity of our climate models, also, as we increase that, that consumes more of the computer calculations. And then the final element of how we spend the calculations is the number of simulations we do. So what we tend to do now, rather than just running one projection of the future world, we run dozens. And the way we do that, we change the model slightly to give us a sort of envelope of confidence, if you like, or spread in the possible futures. So resolution is one factor, and there's been a big drive in increasing the resolution of climate models, which I alluded to over the last 5 years or so. And I think we're beginning to get to a place where we'd like to be. Now, at the end of your question, you said that you're right, for some of the university applications, we'll have to run lower resolutions, but that's a computer resource issue, I think. Sorry, it's a slightly rambling answer, but I hope I've addressed your question.
And Eleanor, do you want to answer about the
question about
question?
in situ high resolution observations? There was an oceanographer, one of the, I suppose, the fathers of oceanography, Henry Stommel, who in the 70s, I believe, envisioned the future of ocean observations. And in particular, he envisioned what have now become gliders, underwater gliders, buoyancy-driven vehicles, doing some sort of, he called it a cotillion, which I don't know if that translates into the UK. It's like a dance that you do in the US when you don't want to. A cotillion of gliders profiling back and forth across the Atlantic, replacing ocean ships, seagoing ships, and making what would then be high-resolution observations across the Atlantic. And as they crisscross in their paths, you can do data calibration between them. I think what we have now is the Argo system, which is designed to measure the oceans at approximately 3-degree resolution, 300 kilometers, and 3 monthly timescales. I don't see that that's going to be replaced with high-resolution in-situ observations. Maybe if there were an understanding of how that would change our understanding of the oceans or our prediction of the future, there may be a push for that, but the current gaps in the deep ocean may be more pressing. You did say in situ observations as opposed to satellite, but there are advances in satellite oceanography that are going to give much higher resolution views of surface currents.
I'm going to have to draw this to a close now, but we're going to continue the discussion informally. So I'd like to thank all our speakers and our panel, first of all.